Okie doke, we're going to do the problems that you see written here from the review packet. The first one on page 2, number 11, is about a basketball player who jumps straight up to grab a rebound. She's in the air for 0.8 seconds. How high does she jump? All right, I'm going to set up another chart, and the key thing here, I'm going to first of all draw a sketch. Here's the floor. Here's the basketball player who looks a lot like a ball, and she jumps up in the air and comes back down in a total time of 0.8 seconds. But they're interested in how high does she jump, and that happens up here. So what we really, this is the whole time, what we have to recognize is that we're actually only interested in half of this whole trip, from the tippy top to the ground or vice versa. So we have to take that time they gave us and cut it in half, 0.4 seconds, because that's how much time she spends going up or coming down. I'm going to just have I'm going to find her final height by seeing how far she drops. I'm actually going to do from the tippy top. This is her velocity initial at the tippy top, which is going to be equal to 0. And then I'm going to have see how far she travels on the way down to just before she lands. So for me, I'm going to say that the initial velocity is 0. Her acceleration, of course, is 9.8 meters per second squared down. And I'm interested in D, how far does she fall, because that'll be tell me how high she was when she started on the way down. Okay, I'm going to use the formula D equals VIT plus 1/2 AT squared. I arrow 0 that, and I end up just calculating 1/2 times 9.8 meters per second squared times 0.4 seconds, and that has to get squared, and when I do the math, I get an answer of 0.78 meters. Okay, page 5, number 12. I'm looking for page 5, number 12. Okay, this is two carts crashing into each other, and then they go rolling off. This is a collision between two carts, and they ask me for the final speed. We're talking about conservation of momentum. So this is number 12, page 5, and so I'm going to start off with the P before equals P after, but I'm really going to start with the full version of that, which is M1V1I plus M2V2I is M1V1F plus M2V2F. And now I'm going to read the question and see what the heck they give me here. Okay. The first cart that's moving has a mass of 1 kilogram. I'm going to call that M1, 1.0 kilogram. And it's moving with a speed of 0.5 meters per second. So I'm going to give that V1I of 0.5 meters per second. When it collides with a second 1 kilogram cart, so M2 is 1 kilogram, which is initially at rest. So V2I is 0. And then they stick together, and they want the combined speed after the collision, which is VF. So the simplified step here with this momentum formula has me looking for two things. I'm looking for zeros, and I have 1 with V2I, so I'm going to arrow 0 that term. And it has me looking for stuck togethers, which I have here because the carts are stuck together. So let's see how we deal with that. First of all, on the left, I arrow 0 that term, so I have M1V1I is the only thing left. On the right, because these two carts are stuck together, they both have the same final velocity. So basically, it's not V1F or V2F, it's just VF. And what that means is I can factor it out, and I have M1 plus M2 in parentheses because I factored out the VF. Conceptually, what I have here is actually one object. I have one big cart of mass M1 plus M2 times its velocity. If you want to look at it that way, I only have one object after the collision, which has a mass of the combined mass of the two carts. Okay, now I want to find VF. I will Sifu this, and I get VF. I'm putting all those nice colors. I'm going to divide both sides by M1 plus M2, and I get M1V1I over M1 plus M2. Now I'm ready to put in numbers. 1 kilogram times 0.5 meters per second, all divided by 1 kilogram plus 1 kilogram. And that gives me a final answer of 0.25 meters per second. Okay, that takes care of number 12. The next one I'm doing is page 6, number 14. Okay, so page 6, number 14. Okay, this is another collision In fact, this one I'm going to say is very similar to the last one. In terms, it's just a clay and a steel block instead of two parts, and the numbers are different. So I'm actually going to go back and steal this equation because I'm using it again. That's pretty lame on my part. And the difference here is in the numbers. So let me out number 14. M1 is the clay. M1, I just misspelled M, is 1 kilogram, and it has an initial velocity of 6 meters per second. M2 is the steel block, 3 kilograms, and it has an initial velocity of 0, and they're looking for final velocity. The simplified step is the same. I arrow 0 that term, and these two velocities on the right are the same as each other because the clay is stuck to the steel block. They both have the same speed. So I have M1V1I is, and I'm going to factor out that VF, M1 plus M2. And I divide both sides by M1 plus M2 to find VF. And I get M1V1I over M1 plus M2. And when I plug in the numbers, I've got 1 kilogram times 6 meters per second, all divided by 1 kilogram plus 3 kilograms, M1 plus M2. And I get a final velocity of 1.5 meters per second, which is choice A. Okay, finally on this video we have, give myself some room, on page 7, numbers 18 and 19, which are similar to each other. We're talking about a gravitational force between two objects. So here's M1, and here's M2, and they're a distance r apart from each other, measured center to center. And number 18, they call these A and B instead of 1 and 2, with the same basic idea. And I'm using the gravitational force formula between any two masses anytime, which is big G M1 M2 over r squared. And basically what they're doing in 18 and 19 is they're saying, what happens to the size of this force here if the numbers over on the right-hand side change? And so you can do this, really the easiest way is to just make up numbers on the right-hand side and change them the way they tell you to change them. So I'm going to do that. I'm going to start off, so I'm going to actually do like a before and after, because we want to compare the new force to the old force before we change things. So before we change things, I'm going to make up numbers for everything on the right, and I'll make up the easiest numbers I can. I'll make up 1. Even for big G, I'm going to say it's 1. And the mass of the first object is 1. And the mass of the second object is 1. And the distance squared is 1 squared. So the original force is 1 times 1 times 1 over 1 squared is 1. The new force, Fg, is when the mass A is doubled and distance r is tripled. So I'll change those things. I won't change everything though. So this is the new force. Let's see. The formula is big G M1 M2 over r squared. Remember, I'm not putting in numbers to get an actual answer. I'm just putting in comparative numbers to see how the force changes. So big G, that doesn't change. It's a constant. It's still 1. M1, well, one of these masses was doubled. So for M1, I'll put in 2. For M2, I'll put in 1 because they only changed one of the masses. And then the distance is tripled, so I'll put a 3 in the bottom, and that gets squared because r gets squared. So my new force is, let's see, 1 times 2 times 1 is 2, over 3 squared is 9. My new force is 2/9 compared to the old one. And so that's why the answer is choice A, 2/9. And finally, the very last question, which is number 19, on the same page. Same basic idea as 18. And so I'm going to just reuse what I have here. The original force, before I change it, is 1. The final force is formulas G M1 M2 over r squared. The constant doesn't change. In number 19, they doubled both masses. So I've got times, I'm sorry. So I've got times 2, because we doubled the mass, times 2, because we doubled the mass, but they're still the same distance apart. And so that gives me a new gravitational force of 1 times 2 times 2 is 4, divided by 1 squared is 4. So again, this tells me that the new force is 4 times the old one. Well, the old force was 20 newtons, So the new force is 4 times 20 is 80 newtons, and we are done.